Welcome to this video on Chemical Ideas 6.1, which is all about the way that light interacts with electrons in atoms. While we go through the video, I suggest you have Chemical Ideas 6.1 open in front of you and follow through to help make sense of some of the ideas. So firstly, a little bit of revision. You should know that we can think of light as being made up of waves. We can say that light is a wave. It's a form of electromagnetic radiation, and as you know, it has a characteristic wavelength, and we denote wavelength with the symbol lambda, Greek letter lambda, and a characteristic frequency, which we give the Greek letter nu. So here's our electromagnetic spectrum, and you know that visible light comes somewhere in the middle, and it's split up into 7 different colours, and each one of these different colours has a different frequency and a different wavelength. What do we mean by wavelength and frequency? Well, you should remember that wavelength is the distance travelled by a wave during one complete cycle, and we represent it by the distance between 2 consecutive peaks or 2 consecutive troughs in the wave, whereas frequency tells us how many cycles a wave goes through every second. Wavelength is measured in meters normally, and frequency is measured in hertz, or units of seconds to the -1. Now all of this is true of any wave, but when we're thinking about electromagnetic waves, we need to consider something else. You should be familiar with the idea that for a given medium, light will always travel at exactly the same speed. If the medium is a vacuum, then light travels at 3 × 10⁸ meters per second. We say the speed of light is invariant. And there's a simple relationship between the speed of an electromagnetic wave, which we call c, its wavelength lambda, and its frequency nu, and they're related by this equation. The speed of light is equal to its wavelength multiplied by its frequency. C equals lambda nu. What's really important to remember, because we know that the speed of light c is invariant, as we increase the wavelength, we must therefore decrease the frequency. So waves with a long wavelength also have a low frequency, and vice versa. Waves with a high frequency must have a very short wavelength. Something you might not have come across before is something that's called the particle model or the particle theory of light. And this was put forward by Einstein in the early 20th century because he'd observed some phenomena that just couldn't be explained if you thought of light just as being made up of waves. Instead, he put forward the idea that you can also think of light as being made up of particles that we call photons. And these particles have a certain amount of energy, and whereas before we said the frequency of light corresponds to the colour or the region of the electromagnetic spectrum, instead we can think of the energy of the photons as corresponding to the particular colour of light or region of the electromagnetic spectrum. Another way, if it helps, you can just think of photons as being packets of energy. They are particles, but they don't have mass. But they can interact with matter, as we're going to see. Crucially then, we can link the particle and the wave models of light by using a really important equation. And that's this equation here, which states that the energy, E, of a given photon is related to its frequency, nu, by multiplying the frequency by this number here, h, or Planck's constant. And Planck's constant has a value of 6.63 × 10⁻34. So Max Planck, after whom the Planck constant is named, is a really important quantum physicist, and he proposed this model also in the early 20th century. And why is this important? Well, this is really important because what it tells us is that if we know the frequency of any wave, we can work out how much energy it's got. Again, if we look at what this equation is telling us, well, we know that if we've got a photon of high energy, then that corresponds to light of high frequency. So it's really important that you remember that high frequency waves are also high energy waves. You should remember that if waves have a high frequency, they also have a short wavelength. So high frequency, short wavelength, these parts of the electromagnetic spectrum have high energy. So far this all seems a little bit abstract and theoretical, but it relates very, very closely to experiments that you've almost certainly done before. So if you've done a flame test, you will have seen that atoms can emit light when they are heated. So why should this be the case? Well, if you heat an atom, you are supplying it with energy. You can think of heating atoms as causing them to absorb energy. So you take your sample of atoms, or usually ions, and you put them in a flame, you heat them up, they're absorbing energy. And the posh word for this is to say that they become excited. Okay, so your atoms absorb energy and become excited when you heat them. However, they don't stay that way. What happens next is we have our excited atom. It would rather be lower in energy. So it emits that energy and goes back to being what it was before, what we call the ground state, or the not excited state of the atom. When it emits this energy, it emits it as electromagnetic radiation, often visible light. And this is what's happening in a flame test. So this shows a flame test of a sample containing copper. And what's happening is the ground state copper atoms absorb energy, then emit this, and in this case they emit this as electromagnetic radiation, which corresponds to green light. So it has the characteristic energy and frequency of green light, that part of the electromagnetic spectrum. But there's something far more intriguing than that going on. So if you take the light that's being emitted by the atoms in a flame test and analyse it by passing it through a prism or a diffraction grating, as you can see in the diagram on page 120 of Chemical Ideas, what you notice is that you don't just simply see a continuous spectrum of light. Instead, you get what we call an emission spectrum, which contains coloured lines, so a series of sharply defined coloured lines on a black background. And the reason that these lines are sharply defined is because the atoms are only emitting certain precise frequencies of light. Actually, this emission spectrum here corresponds to the emission spectrum of neon. And you've heard of neon signs, they're bright orange or bright red. And if we look at this emission spectrum, most of the lines that neon is emitting, or most of the light that neon is emitting, is in the red-orange region of the visible spectrum, the sort of lower frequency, lower energy end of the visible spectrum. And that is why when we heat up neon, it emits orange-red light. It emits these certain precise frequencies of light. So remember, when you heat up atoms, they emit light. The light that they emit is only at certain precise frequencies, and if we split up that light, we see that it's a series of coloured lines on a black background that we call an atomic emission spectrum. Let's take a different experimental setup. Let's say if you gently heat some atoms, this time they aren't going to become excited. They're for the most part going to stay in the ground state. But if you then take your ground state atoms and shine white light on them, they can now absorb the energy of the light. And they become excited, as we saw before. Here's our excited atom. This time, if we analyse the light that's coming through the sample, we're going to see the reverse situation. Most of the light is just going to pass straight through the sample, but some of it is going to be absorbed. And these black lines on the spectrum correspond to where the atoms are absorbing energy to go from the ground state to the excited state. We call this an absorption spectrum. So black lines on a continuous spectrum where the black lines correspond to the exact frequencies of light that are being absorbed by atoms. This is what we mean by an absorption spectrum. The process of analysing atoms in this way is called atomic spectroscopy, and it's incredibly useful for the following reason. We were talking about neon. Here's a slightly more detailed picture of the emission spectrum of neon. Every time you do an atomic emission spectrum with neon, you will get exactly the same frequencies of light being emitted. So exactly the same colours, lines in exactly the same position on the emission spectrum. And if you did this with any sample of neon, you would always get the same emission spectrum. And if you used a different element, you would get a different spectrum. If you like, atomic spectra are like fingerprints of a particular element. And they can be really useful. So you can use these atomic spectra to identify the elements that are present in a sample. Let's say you don't know what elements are in an unknown material. Note as well that the exact lines that appear as coloured lines on a black background in an emission spectrum correspond exactly to the black lines in an absorption spectrum. So the energy that is taken in and absorbed when atoms go from the ground state to the excited state is exactly the same as the energy that's given out when atoms go from excited state to ground state. That's going to become quite an important idea later on in the chapter. So how can we explain these results? How can we explain the appearance of these sharply defined coloured lines on a black background in an emission spectrum? In order to do this, we actually need to explore some new concepts that you are unlikely to have come across before. So let's take hydrogen as an example, hydrogen being the simplest element there is with one proton and one electron. And let's look at its emission spectrum. As we said, the emission spectrum for any element is absolutely characteristic of that element, and this is the emission spectrum of hydrogen, which is sometimes called the Lyman series after the scientist who first observed it. Now in actual fact this contains, or the Lyman series contains lines in the UV, visible and infrared regions of the electromagnetic spectrum, but we are just looking at the visible part of the Lyman series. These 5 lines, and they're absolutely characteristic of hydrogen. So where do these lines come from? Well, it wasn't until 1913 when a Danish scientist called Niels Bohr put forward an explanation for where these lines come from. And as I said, to do this, we need to look at some ideas that we haven't thought about before to do with the principles of quantum mechanics. We're going to do that next lesson. Before doing that, I suggest you answer the questions in the Think section of this video. And also, I suggest that you read through Chemical Ideas 6.1 again to make sure that you're comfortable with where atomic spectra come from and what they are.